Hello, everyone. Good to have you back again. This is Module 2 of Thinking Critically, Interpreting Randomized Clinical Trials. In this module, we're going to focus on how to analyze data from RCTs. This will be helpful because when you read a paper, you need to feel comfortable in interpreting what the results are. So before we begin talking about how these various measures are estimated, let me ask you a question. So at the end of a randomized clinical trial, who should be included in the analysis? Only those who completed the study? Only those who completed the study and were compliant with protocol requirements? Or everyone who was randomized? And you are right. The answer is everyone who was randomized. Now, why is that? So by the way, this approach, where in RCT everyone who's randomized is analyzed, is referred to as intention to treat. Why is ITT considered the gold standard? Because it ensures that balance of measured and unmeasured confounders that was initially achieved through randomization is maintained and preserved in the analysis as well. Some also will argue that because in real life some patients may not adhere to all the treatments that you're recommending them to, that ITT sort of permits evaluation of effectiveness, not just efficacy, by sort of simulating what happens in real life. But this has implications, because if the gold standard is intention to treat, we want to make sure that there's high compliance of the study subjects to the treatment that they were randomized to, and that the follow-up is excellent. So you've collected outcome measures on everyone in the trial. Now let's look at what are the common comparisons that are made in a randomized clinical trial. Well, if the outcome is binary, such as risk of dying or risk of an event, then often you might see comparison of risks or rates. Often, if time to event is relevant, such as time to a cardiac event or time to recurrence of an infection or a relapse in, say, multiple sclerosis, you might see survival analysis techniques being used. And if our outcome measure is continuous, such as looking at weight loss or changes in cholesterol levels, then there the study will be interested in comparing means between the two study groups. So let's go back to the schema that we saw. We saw in a clinical trial, you start with subjects who are randomly assigned treatment, and the other half may get the placebo treatment. And then you follow up the subjects over time and see how many in the treatment group develop the outcome. So here I sub E is nothing else but the risk of the outcome in the treated group. Similarly, I can define I sub E minus as the risk of the outcome in the placebo or comparison group. Now, what do I do with these two risks in the two groups? Well, I can compute what's known as a relative risk. And in this case, where I'm comparing risk in the treatment to the risk in the placebo arm, I'm just using a ratio of two risk estimates. And so in this 2x2, where you can see in a clinical trial, I may start with A plus B subjects that were assigned the treatment and C plus D that were assigned the placebo. The numerator for the relative risk estimate is the incidence or the risk of the outcome in the treatment group, and the denominator is the risk of the outcome in the placebo group. Now remember, a risk can only range from 0 to 1 since it is nothing else but a probability of the outcome. Now, sometimes in a trial, people will actually compute not just the risk, but the incidence rate of developing the outcome in each arm. Now, what is an incidence rate? The numerator is similar to your risk computation, where it's just the number of subjects who develop the outcome of interest during the study. The denominator, however, in the rate is the number of person years of follow-up where the individual was at risk for developing the outcome. So to demonstrate that, I'm going to give you a really easy example. So let's say a trial was designed for 4 years. Now, subject number 1, shown here in this red bar, started the study at time 0, was followed up for the entire duration of 4 years, and never developed the outcome. So this subject would contribute 4 years in the denominator for the rate computation. Now, this subject in green started the study and developed the outcome approximately at 1.5 years. So this subject would contribute 1.5 years in the denominator of the incidence rate, because once they've developed the event, we're not interested in them developing the event again. So their clock stops now. And finally, we've got this third subject in blue who's just stayed in the study for 3 years, didn't develop the outcome, and then dropped out of the study. So this person contributes only 3 years in the denominator. So what we do for the incidence rate denominator is we sum up the years that each subject is in the study prior to developing the outcome. So the advantage of using the incidence rate then is you can actually account for varying amount of follow-up in study subjects. Now, if an incidence rate is being reported, then people will compute what's known as a rate ratio, which is a ratio of the incidence rate of the outcome in the treatment arm divided by the incidence rate in the placebo arm. So note that A is the number of events that occurred in the treatment arm, and X now is not just the number of people that you started with in the treatment arm, but it's the actual person years that people contributed while they were in the treatment arm. And likewise, C is the number of events in the placebo arm, and Y is the person years of interest in that placebo group. Note that the time dimension, the person years, drops out in both. Since it appears both in the numerator and denominator, they cancel each other out, and you're left with a dimensionless quantity, which is interpreted just like the risk ratio. And so RR stands for relative risk, which could be formed either using 2 risks or 2 rates. So the null hypothesis for the relative risk takes on a value of 1, which would imply there's no association between the exposure and the outcome, and that is our null hypothesis. When the relative risk is less than 1 and we're looking at a harmful outcome, this would suggest that the intervention is a protective factor because it's reducing the risk of the outcome in the treatment arm. On the other hand, when the relative risk is greater than 1, it would suggest that this particular intervention is actually a risk factor for the disease. Now, oftentimes, when time to event is relevant, you will see what's known as a survival curve. What is a survival curve? It actually depicts events as they occur over time. It tells us how rapidly events are occurring over time. It also has the advantages that it takes into account varying follow-up time, because we know not everybody develops the outcome at exactly the same time, and that some subjects do drop out from the study. What does the survival curve give us? It allows us to estimate the median survival duration, which tells us, what are the percentage of survivors, when half the people are alive and half are dead, and, what's that time? But it also tells us the percentage of survivors at any time along that time axis, which is usually on the x-axis. So here is a hypothetical example where a cohort of about 36 subjects was followed over 36 months or 3 years. And the survival curve, also known as the Kaplan-Meier curve, is a step function. So every time an event occurs, you see that there's a dip in the curve. The double dip here suggests that 2 events occurred exactly at that time point. So what types of information can we estimate from this survival curve? Well, the first one is if I just wanted to know at the end of the study period, that's at 36 months, how many people, what is the probability or the cumulative risk of surviving this event? Well, as we can see, at the end of the study, I go across with this horizontal line to the vertical axis where I have the percent alive. I notice that, 40% of the people survived at the end of the study, which means that the probability of dying in this particular example is 60% over the 3-year period. The other measure of interest, as I mentioned, is the median survival, where we want to know what is the time at which 50% of our cohort is still alive. And so if I take this horizontal line from the y-axis, where it's 50% is the proportion that survived, drop it to the curve, and then drop that vertical line down to the time axis, I can see that the median survival in this cohort is about 24 months. Now, in the Diabetes Prevention Program study, which I had introduced in the introduction, which I had mentioned, just as a reminder, it was a 3-arm trial where subjects with insulin resistance or impaired glucose tolerance were randomized to either the placebo or to get metformin or on a lifestyle intervention. And what you're seeing here is instead of a survival curve, you're seeing a cumulative incidence of diabetes curve, which is sort of the flipped version of the survival curve. And it gives you the cumulative risk of developing diabetes over the study period. So let me ask you a question. Suppose if I asked you at 3 years, what is the relative risk of diabetes in the lifestyle group compared to the placebo group? And I've given you some numerical answer choices. So take a few seconds, get out your calculator or do mental math and try to figure out how would you go about estimating this relative risk. Okay, so hopefully you all have paused the video and done the quantitative analysis here and come to the answer of 0.5. So how did we get that? Well, at 3 years, into the study, I drop this vertical line going up that touches all the 3 curves. I then take a horizontal line to figure out what was the risk of developing diabetes in people who are randomized to the lifestyle intervention. And we see that it's approximately 14%. Well, for the placebo group, if I do exactly the same, use the same algorithm, I come up with an estimate of 29%. So what is the relative risk at 3 years of developing diabetes in the lifestyle group, which is 14%, compared to the placebo group, which is 29%? It's approximately, 0.48, which corresponds to answer choice C, which is 0.5. So how do we interpret this? That, if you are randomized to the lifestyle group, after 3 years, your risk of developing diabetes is reduced by 50% compared to those individuals who are randomized to just the placebo arm. Another term that might be useful to you as health professionals and clinicians is what is the number needed to treat. So the number needed to treat is literally the number of patients who need to be treated in order to prevent one additional bad outcome. And it is nothing else but the inverse of the absolute risk reduction. Well, what is the absolute risk reduction? It's nothing else but the arithmetic difference between the incidence in the unexposed group, which is the placebo group, and from that you remove the incidence or the risk of developing the outcome in the treatment arm. So what is the NNT? It is nothing else but the inverse of the absolute risk reduction, so it's 1 over ARR. Now let's try to estimate that using our DPP study. So if I wanted to know from this figure that gives me the cumulative incidence of developing diabetes in this particular study, what would be the absolute risk reduction if I wanted to compare and compute the number needed to treat for lifestyle? Well, as we noted before, the risk of developing diabetes at 3 years is 29% in the placebo arm, while the risk was 14% in the lifestyle group arm. So the absolute risk reduction is 15%. So the inverse of that, which is the number of needed to treat, works out to be 1 over 15%, which is 6.7. How do we interpret this? Therefore, we would need to treat 7 people with intensive lifestyle to prevent 1 case of diabetes in 3 years. Now, the final note I want to make is that clinical trials are often monitored as they progress. And why is that done? Because monitoring the results of the trial during, maybe at year 1, at year 2, and year 3 is important because it can tell us if the intervention is, that it's not producing any harm, in which case, perhaps the trial needs to be stopped. Another reason for monitoring is we want to make sure that, if the intervention is really effective, more than expected, ethically, we may want to stop the trial and provide this therapy option to everybody in the study because it would be unethical to hold back this highly effective treatment. And finally, we monitor clinical trials if we feel that, there's no possibility of answering the research question. So why would you want to waste resources and subject all your study subjects to these interventions when there's no hope of finding a signal. So in this module 2, we have reviewed approaches for analyzing data from RCTs. We've talked about the relative risk as it may be estimated using 2 risk ratios or 2 rate ratios. We've talked about the absolute risk difference and number needed to treat. And although I haven't given you a specific example, just keep in mind that if the outcome measure is continuous in nature, the researcher might be reporting a difference in these 2 group means. So thank you, and I'll see you back in Module 3, where we will now go through the critical steps involved in evaluating the validity of a randomized clinical trial.